So we are so excited to have you here. We're gonna get started. We've got Illinois. Okay, I gotta stop looking because then I get distracted and I get so excited. So welcome everybody. My name is Sarah Eckert. I am a communication specialist in the Office of Polar Programs at the National Science Foundation. I have the absolute pleasure of working with an incredible group of researchers and support staff in the U.S. Antarctic Program. So the U.S. Antarctic Program is operated by the National Science Foundation, and we operate 3 permanent research stations in Antarctica, as well as research vessels that travel around the Southern Ocean, around Antarctica. And then we also support field camps during the summer. And I know that our presenters are going to be talking about probably some of those field-based science, not necessarily at our 3 stations. But if you're just joining us and you haven't had a chance, please drop us a note in the chat where you're tuning in from, who's with you. We love to see where everybody is joining from, and we will kind of get started. So just some quick housekeeping notes. Everybody is muted without video, just for bandwidth purposes. We hope you understand that. We are going to have time for Q&A. So please use the Q&A option via Zoom. You should be able to upvote as well. So if you see a question that you also have that you really want answered, definitely give it a thumbs up to upvote it. We'll try and get to them. We may not be able to get to all of them, but we will do our best. And then finally, this webinar is being recorded. After the event, we're going to send an email to everybody with a link to the event, as well as a bunch of resources you can use to find out more about Antarctica, the U.S. Antarctic Program, and the science we're talking about today. So I want to introduce our 2 presenters today. So we have Dr. James Karner and Dr. Jenny Radabot, and both of them are joining us from Utah. So we've got Dr. K is at the University of Utah, and Dr. Radabot is at BYU, Brigham Young University. I was like, I know the abbreviation really well, but I have to make sure I remember that. So both of these researchers are absolute titans in planetary and meteor Antarctic science. Actually, Dr. Radabot just had a asteroid named after her, so I think that's pretty cool. So we'll give her an applause, which is fantastic. And so we're so glad to have you guys joining us today, talking about the Antarctic Search for Meteorites program and your work in Antarctica. So I'm going to stop sharing the screen here, and I'm going to turn it over to you, Dr. K, and we will get going.
Okay. I think we're good. You guys can hear me, I hope. Janie,
Yeah,
give me a thumbs up. Okay. And then there's just one more thing I have to do. I have to share sound. And okay, I'm doing that already. And then I think we're ready to go. So thank you for being part of this talk today and letting me explain the Antarctic Search for Meteorites program. A little background, we are a NASA-funded grant where I'm the co-principal investigator along with Ralph Harvey at Case Western Reserve University in Cleveland, Ohio. This program, this search for meteorites and curation of meteorites after we bring them back to Texas or the United States, is supported by NASA. We have been funded by NSF, the National Science Foundation, in the past, and we certainly collaborate with the National Science Foundation. They provide the logistics and the can-do so we can get into the field in Antarctica. This first shot is a picture of what we affectionately called the beach in the Davis Ward region of Antarctica. You can see the ice surface here, but then you can see this big a moraine, a collection of lots of terrestrial rocks, and there's lots of meteorites in there. And we have the team searching for them here. And I'll just point out that all these little red flags that you see in the background and the foreground, those are meteorites we found in the beach. So this was a really productive area to recover meteorites from. Whoop. Okay, so what is a meteorite? A meteorite is a rock in space. It starts a rock in space. It streaks through our atmosphere. Sometimes it shows a fireball, like this picture taken in right over Salt Lake City in 2022. And if it lands on the ground in a piece that you can find, it's called a meteorite. And that's actually the Great Salt Lake Meteorite. It was here streaked over Utah in August of 2022 and landed on the ground near the Great Salt Lake of Utah. So that's a meteorite. What are the different types of meteorites? Most are stony meteorites, and we call these chondrites, and they look like this picture over here on the right. They have a brown fusion crust on them usually, and they're called chondrites because they're filled with chondrules, which are little silicate BBs, little rocky BBs in there. They make up about 90% of all meteorites. A smaller number of meteorites are stony irons or iron meteorites. They're basically made of all iron nickel metal. You can see this cut piece here from the Smithsonian where they cut it in half. You see that bright, shiny, silvery metal. That's the iron nickel metal. And then 5% of meteorites are similar to volcanic rocks on Earth, and they're called achondrites. And we'll get into these a little more as the presentation goes along. So where do meteorites come from? And I will say that this presentation is meant to be a little interactive with the audience, but since I can't hear you or see you, I'll assume that you guys are playing along at home. So when there's a prompt, I'll give you guys a couple seconds to get some answers in your classroom or your living room or wherever you're turning in from. So where do meteorites come from? We know they come from at least 3 specific solar system bodies. So what are those bodies? Well, most meteorites come from, and these are pictures of 3 different kinds of this planetary body. I'll give you a chance to think. Most of the time, these planetary bodies have a weird shape that's not spherical. They might be dumbbell shape or potato shape, people say. Those are actually asteroids. Most meteorites come from asteroids. And an asteroid is a rock in space. It's usually in the asteroid belt. But sometimes these asteroids get tugged out of their orbits, and they basically, instead of a circular orbit around the sun in the asteroid belt, they now have an elliptical orbit that takes them really close to Earth in their journey around the sun. And you can see that in the fluorescent green orbit here. Those rocks, those asteroids are called near-Earth objects, NEOs, or near-Earth asteroids. And we hear a lot about those in present times, that something is a near-Earth asteroid or near-Earth object is passing close to Earth. You might have seen that on your phone. Every few months, it seems we get a notification that an asteroid is coming really close to the Earth. Those are also the sources of most of the meteorites that are sucked into Earth's gravity well and land on Earth, near-Earth objects or near-Earth asteroids. We also have meteorites from this body, number 2. And there's a nice picture of it, photograph of, you guys all know, I think that's the moon. And then the third place we have meteorites from, third planetary body, is Mars. Okay, so why are meteorites important for science? And I'll just go through a couple importances from each of these planetary bodies. Like I said, most meteorites are from asteroids, and being from asteroids, these meteorites tell us about the beginning of the solar system, 4.56 billion years ago. These, a lot of times these meteorites are the first solids of our solar system. So they take us to a time and record ages that we don't have any recordings of here on Earth. All the rocks are younger than 4.56 billion years. So people use these meteorites to study the beginnings of the solar system. And sometimes they can even find grains in there, little silicate grains or minerals that are from before the solar system started, before 4.56 billion years. We also have a lot of meteorites from the moon, 100, 200 or so now. We recognize that are from the moon. And these allow us to study parts of the moon that the Apollo astronauts or the lunar landers didn't get to. Remember, they only got to about 8 sites, but we actually have meteorites from the moon that are from all over the surface of the moon. And lastly, we have meteorites from Mars. And we have about 100 or so pieces of Mars that have landed on Earth. And these provide ground truth to what's really up there on Mars. Right now, today, we have landers and orbiters and even helicopters on the surface of Mars. They're looking at the composition of the rocks on Mars, looking for scientific data they can glean from the surface. These meteorites from Mars provide ground truth to what that rocks are that actually are on Mars. And a bonus for meteorite science is that they allow us to study other planetary bodies without ever leaving our planet. Okay, so where do you find meteorites on Earth? This is just a printed map that I have from a grad student way back in the 90s. He made this and gave it to me. And I don't know if it's ever been digitized, but up until this time, about 1997, there had been about 2,000 meteorites that had been found in the United States. And I always ask this question, where does it look like most of the meteorites are found? I have the Great Salt Lake, orange or red dot there. But most of the meteorites found in the United States are right through the central part of the continent or the country, from Texas, Oklahoma, Kansas, and up through Nebraska. There's just a vast amount of meteorites. And when we think about why we could find a lot of meteorites there, it turns out that that part of the country is very sparse in vegetation. It's high desert. There's not a lot of trees. There's not a lot of grass. There's not a lot of leaves. There's not a lot of wet weather that's going to erode meteorites once they are hit the ground. So basically, the conclusion is meteorites concentrate on stable, old surfaces with slow or negative rates of terrestrial accumulation. And that's just a really fancy way of saying there's no grass, there's no trees, there's no bushes, and there's little precipitation. So this means they're found in hot and cold blank. Give you a chance to think about that, but the answer is deserts, hot and cold deserts. Antarctica is the ultimate cold desert. Here's a RadarSat image of the continents. It's covered with ice. Remember that Antarctica has a continent under it, but it is covered with ice. At the South Pole, kind of right in the middle of the continent, the ice is about 2.5 miles thick. So very thick covering of ice. It's been covered with ice for about 35 million years, around there. So in those 35 million years, when Antarctica has been growing ice on its surface, meteorites have been raining down. And if you think of Antarctica as like an overturned bowl of ice, the ice is sliding off the continent towards the coast. Meteorites have been landing on the surface of Antarctica. They've been buried with snow. They basically are buried in the snow, encased in the ice, and then they flow with the glaciers that are flowing out of Antarctica. And right along here, up from my red dot here, that is McMurdo Station, you see there's a mountain range in Antarctica. Those are the Transantarctic Mountains. They poke through the ice at about 14,000 feet. So meteorites rain down on the surface for millions of years. They're carried in the glaciers towards the periphery of the continent. And in these places where there's obstruction to the glacier flow, the glaciers are slowed down and basically the ice is whittled away at the surface, slowed down, whittled away, and the meteorites pop up at the surface. And that is the great concentration mechanism of meteorites in Antarctica. Here's a cartoon of that process. You have the falling meteorites onto the glacier. They're being buried. They're being swept up in the ice movement, and they're basically being carried with the glacier until they hit the mountains, either poking out at the surface or maybe subsurface topography. Those glaciers are slowed down. And this is where, at the foot of those mountains, where they're being stalled, we get blue ice areas. And this blue ice is the color of the ice, but it just means that deep ice is being exposed as the surface is whittled away, and the meteorites are being exposed also. Here's a satellite image of that blue ice. You can really see it's a great, beautiful blue color. The dark colors here on the right side of your image are mountains. Those are the Allen Hill Mountains. And if you envision the ice moving from left to right on your screen, basically this ice is being stalled by these mountains and being whittled away, and blue ice coming up to the surface. And that's where we find those meteorites. Here's a meteorite on this blue ice. You can see it's that beautiful blue color, and it's also very rough. It's what we call scalloped by sun cups. And there's a nice black meteorite, easy to see on this light blue ice. Okay, so our trip to Antarctica starts with Antarctica here on the bottom of Earth. You can see New Zealand here in relation to that. And then on the Antarctic Peninsula, you can see how close South America is to that part of Antarctica. We go to McMurdo Station. We usually take off from the west coast of the United States. We fly on a long flight, about a 14-hour journey down to New Zealand. We actually get to Christchurch, New Zealand on the South Island, and then we're going to go from there to Antarctica. We're going to stop in New Zealand and get our clothing and some other training. Here's a map on the right side, shows this in a little more detail, Christchurch, and then the flight all the way to McMurdo Station, and then eventually a flight out to the Transantarctic Mountains where we're going to hunt for meteorites. This is the Clothing Distribution Center in New Zealand. This is where we get all our clothes for this cold expedition we're about to embark on. These clothes on the wall, although this is pictures from the 90s, you can see all the different clothing and gloves and hats and pants that you get at this Clothing Distribution Center. And this is also where you get Big Red. This is maybe the most famous piece of clothing from Antarctica. It's your big parka that you get issued. They are really good bomb-proof parkas. They keep you warm in several degrees negative temperature in Antarctica. And there's the supply you have to choose from in Christchurch, New Zealand. The ice flight, basically you take a military aircraft down from New Zealand all the way to McMurdo Station, either a C-17 or a C-17 or a C-130 aircraft. They're cargo aircraft, so they're basically just a big hollow shell in here, and you have not too comfortable seating for your trip to Antarctica. But 10 hours later or less, if you get lucky and get to take a bigger C-17 than a 130, you land on basically the ice shelf in Antarctica at McMurdo Station. And here is a new Antarctic scientists getting off the plane there. But you can see that we just land right on the ice shelf. It's not paved or anything. It's just groomed, so it's nice and flat, so these aircraft can land there. Here's our destination. This is McMurdo Station, another view of Antarctica from a satellite photo. And I'll just point out that you see these black spots poking through the ice as I go to the right in this picture up from McMurdo Station. Those are the Transantarctic Mountains in Antarctica, and that's where we're going to hunt for meteorites. So we get to McMurdo Station, we have some training to do. McMurdo Station is like a little college town, kind of industrial college town. It's on a volcanic island. It's called Ross Island. And you can see here the various buildings we have. This is where NSF has set up its shop. There's about 1,200 people here in the summer months, and they are all geared towards helping out scientists get out into the field or do their science around McMurdo Station. Our group is going to go out way into the Transantarctic Mountains for 5 or 6 weeks, like I said. So we have to be pretty self-sufficient out there. We pack all our food, our dry food in this photograph on the right. There's Katie Joy, a past participant, making out her food list for 5 weeks supply of food. There you can see we just pack all our food in these coolers. And there's our longtime mountaineer, John Scott, doing some last minute packing on our frozen food. We also get a lot of really good frozen food, all kinds of beef and fish and shrimp and scallops. Very good food from New Zealand to take into the field. We also do some other training in McMurdo Station. We do crevasse rescue training. We do all kinds of safety training. But here I want to take a minute to describe something that's really unique about our project in Antarctica, is that we get to take volunteers on our team of 8 every season. And these, along with myself and Brian Ruggie here, who's our longtime program mountaineer, these volunteers are not paid by the program to go out on these trips, but instead they volunteer their time as a community service to the planetary science community, and they get to go to Antarctica. Now, we also have been able to take non-scientists on our trips. We've taken forest rangers, we've taken journalists, authors, and this year we actually had a woman, Daniela Hernandez, who is a journalist. She got to accompany us and be part of our team that hunted meteorites. We've also taken several astronauts on our program. They enjoy our program to have some kind of training in solitary and isolated environments that meshes well with their duties as astronauts. Okay, so here is our 2 targets that we had for this season, the Davis-Nunatax region and the Main Dominion Range region. On the left here, you see this cartoon map of Antarctica. The blue star down there is McMurdo Station. And then we have to get all the way out to this green square up there at the top of the Beardmore Glacier. That's the Davis Ward area, the Davis-Nunatax and Mount Ward. That's where we're going to search for meteorites. It is about 400 miles away from McMurdo Station, a really long ways by small aircraft, and it's only a couple hundred miles from the South Pole. But once we get out there, we are isolated. We are probably 200 miles from the nearest people on the continent. We've been to the Davis-Nunatax Mount Ward 7 times before this season. In times ranging back to 1985-86, we've recovered over 3,000 meteorites from Davis Ward in that time. Here's a beautiful picture of Mount Ward kind of stretching around the side here in your picture, and then just the scale of the ice that's available to search at Davis Ward. Those are people down there in the middle of the photographs with their skidoos. So huge blue ice areas at Davis Ward, and they've yielded over 3,000 meteorites so far. Here's a map of Davis Ward and the progress we've had over the years. The purple meteorites are meteorites we've found in all previous seasons before 2019-20, and those are the green meteorites. This medium gray color, which all the meteorites are on, denote blue ice. Those are
No, I think he froze. Let's see if he comes back. Oh, there we go.
You can see the vast amounts of blue ice. There's what we call the big tongue, and the width of the big tongue kind of here at the base is about 1.5 miles. So there is a lot of ice available for searching at Davis Ward. Here's our home at Davis Ward for the 6 weeks that we're out in the field. You can see we have 4 living tents, basically 2 people to a tent. And then we actually have a bathroom tent and what we call a science tent where we can gather at night or anytime during the day as a group. We have really nice Scott tents with a vestibule for a little added room. These are the same Scott tents, basically the same design that Sir Falcon, Robert Falcon Scott had in 1912 when he was in a race for the South Pole. And here's one of our team members from that time, Lauren Edgar, out in front of her home for about 5 or 6 weeks. This is what it looks like inside the tent. You can see we use this 2-burner Coleman stove or Century stove for heat. We also use it to make all our food. And you can see it's nice and comfy and cozy in this tent. You're sleeping about 2.5 feet away from someone that's not your spouse or your partner. So that's can be a little daunting to start out with, but generally people tend to get along in our group. We really value that. And here's all the pockets we have. You can really make your tent at home and you can personalize it here. I see Lauren has hung up some pictures of her loved ones there. The main way we communicate with the outside world is this satellite phone down here in the bottom right of your picture. Okay, so how do we hunt meteorites? How do we find meteorites? Well, there's 2 ways we search for meteorites. One is skidoo searching, and basically we call this sweeps, skidoo sweeps. We basically line up about 10 to 20 meters apart on our skidoos, depending on how much rock is on the ice, and we basically just proceed at about 2 or 3 miles an hour down the ice sheet, looking for rocks on the ice that could be meteorites. In this case, if you see something that might look like a meteorite, you might jump off your skidoo to take a closer look. And if it's a meteorite, like this one is here with Dr. Ralph Harvey, you might do your little meteorite happy dance that you came across a meteorite. We also do foot searching in moraines. Now, remember, moraines are kind of collections of terrestrial rock that have been dragged along by the glacier, usually on the sides of a glacier, but sometimes in the middle of a glacier. These moraines contain thousands and thousands of terrestrial rocks, but there's also a lot of meteorites in there, like this one. So you can see all these earth rocks scattered around in this moraine. And there you can see this shiny brown, round, spherical meteorite in their midst. Okay, so I always do a little find the meteorite activity in these presentations as if you all were on our expedition with us. It doesn't take a lot of advanced training to find meteorites. You just have to be good at finding stuff. And you might know if you are or not. Maybe quiz your spouse or your friends on that. Are you good at finding stuff? So I'll give you 3 hints. Meteorites are often darker than any earth rocks around. Meteorites are mostly spherical or at least rounded on all the corners. Earth rocks are often platy and have sharp corners. If you're of a certain age and you remember boxy cars from the 80s compared to cars now that are rounded on all the corners, that might help you visualize how meteorites are. The third hint is a rock that looks different from any earth rock in an area could be a meteorite. So let's get to them. Okay. I'm going to show you some pictures. I'm going to give you a little time to pick out the meteorite in the scene. So I'll give you like 3 seconds. You can play along at home. Okay, there it is. This is a great example of meteorites are often darker than any other rocks around, any of those terrestrial rocks. Okay, hopefully you guys got that one. This is a scene of a well-sorted moraine where just one layer thick, you can see the ice under these rocks, and hopefully you can see the meteorite there. It's right there. Meteorites, especially chondrite meteorites, the most common type, when they weather, they get kind of this chocolate brown appearance. And then you can see kind of some of the inside shining through. It looks a little rusty. So again, a different color than the terrestrial rocks, but also this nice spherical rounded shape. This one here is kind of an oblique view. Not very hard to tell. You can see that brown, blackish meteorite. Now, here's an example where a meteorite has been broken in this moraine, and you can kind of see an angular look to the broken. This is one of my favorite pictures. I'll give you a minute here. There it is, the only rounded, shiny rock in the picture. And this is a great example of terrestrial rocks that you find on glaciers or on the ice is often triangular shape and platy, meaning flat. So this allows you, as an ANSMET worker or searcher for meteorites, it allows you to distinguish between terrestrial rocks and possible meteorites very quickly. When you're on your skidoo, you can look down at rocks and you see if they're very angular or triangular shape or flat, you know that that's not a meteorite. If it's rounded or shiny a little, you might want to take a second look and jump off your skidoo to get a closer look. Okay, next picture. This is a good example of a meteorite that's about twice the size of the terrestrial rocks that it's contained in. So you have kind of a nice wind sorted, all these rocks are the same size here, all these terrestrial rocks, and then your meteorite is about double that size. So meteorites often will be smaller or larger than kind of the median grain size that you're looking at for terrestrial rocks. And last image here, last quiz image here. This might be a little tougher, but you can see this dark rock here, and then something, you have the fusion crust of a meteorite has been chipped away, and you can see a lighter colored interior of the rock. So meteorites will have a fusion crust that's basically it's a melted skin, an eggshell-like crust that forms on a meteorite when it comes through the Earth's atmosphere. And a lot of times when they land on Earth, they'll kind of, that fusion crust will be weathered, and sometimes it's cracked or peeled off, and you can see the inside of the sample. So hopefully you guys did all okay on that. If you're at home, I had 6 images. Hopefully you got all 6 right. We'll see, maybe in the chat, you can report how many you got right out of 6. So once we find a meteorite, we have to document that meteorite. And there's a lot of jobs and a lot of data that we take down when we find a meteorite. First, we note its position on the surface of the ice. With a GPS. We have a snowmobile with a high-resolution GPS so we can get the exact location of the meteorite. Then we have a photographer that's going to take a nice in-situ picture of that meteorite we found on the ice. We also have a counter. We give the sample a name, and then we're going to collect that sample sterilely and note any of its characteristics. We also have to chip a hole for the flag to mark that meteorite, just in case the GPS data is not good. In a couple days, we know where that meteorite was found. It has the number on it. Here, I like to tease that this is astronaut Stan Love, who's a veteran of a couple ANSMET seasons. He loved to chip the holes for a meteorite, and this is the astronaut program. In a gist, basically, is that they get really good at doing one job, and then they practice it a million times over and over, and that's what they do. And so where other people like to trade jobs here collecting the meteorites, Stan was good with just chipping this hole for the flag. We examined the meteorite a little more. Here I've got a magnifying glass. My eyes are not that great anymore, but we're just basically looking for any type of data, any unusual characteristics of the meteorite we can report back to the Johnson Space Center and take in our field notebooks. At the end of the day, hopefully you have a whole bag of meteorites in your backpack. This is Erin Gibbons. She just came back from a day hard working, and she's got about 15 or 20 meteorites that she's going to take inventory of and count up before she puts in this cooler on the far right side of your image. And at the end of the season, hopefully you have a whole bunch of meteorites that you're going to be able to basically inventory, stuff back into your cooler, and send those back to the Johnson Space Center for classification. So this is Lauren Edgar, Erin Gibbons, and Danielle Hernandez basically performing this end of the season inventory of all the samples we've found. Okay, just quick, I'll go over some of them. My favorite meteorites ANSMET has ever found. We have this huge achondrite meteorite. This is actually a meteorite from the asteroid 4 Vesta. You can see this black patchy crust on there. This meteorite is actually one of the oldest meteorites that's ever been on Earth. It has an age, a terrestrial age, meaning it landed on Earth 1.3 million years ago. It's a pretty spectacular found we found in about 2013. These are my favorite images of meteorites that we found from asteroids. We have a big stony iron meteorite here and a iron meteorite there. I've also shown a picture of. This picture at the lower right is a carbonaceous chondrite. That is really valuable because people are studying organics in meteorites and carbon-rich meteorites, those organic molecules and compounds that we need for life. They're really investigating that lately. We have meteorites that we found from Mars. Here's just a few examples of those. You can see they all have this bright black glossy fusion crust, just spectacular looking when we get out into the field and find those. And maybe my favorite samples that we've ever found come from the moon. And this one in particular here with the red arrow, when we found this, we all agreed that this was basically just a miniature picture of a full moon here, where you see these white bits correspond to the white mineral or rock anorthosite on the moon, and the dark bits correspond to the darker places that filled in the craters of the moons. That's the Maria, and that's basalt. So this is like a mini full moon picture, and we immediately knew that was a piece of the moon that we found on Earth. So after the season, we load up our meteorites onto the plane. They're shipped frozen, basically, back to McMurdo Station. And from there, they're shipped on a boat to Texas and the Johnson Space Center, where they will be curated and classified, and then eventually also classified and curated at the Smithsonian Institution. So some of the highlights of ANSMET, what we're all about. We've been to the Antarctic 44 seasons. We've collected over 23,000 meteorites. We have basically recognized the first lunar meteorite, or found the first lunar meteorite. We have the first recognized Martian meteorite was from ANSMET. And about 60 to 70 journal papers per year, every year, are basically get their data from the Antarctic meteorites. So we like to think of us as the world's foremost suppliers of extraterrestrial material for scientific study. And I'll end with this. This is a little bit of a joke here, but it was very, very cold when we pulled out of the field this season. It was actually right about -35 Fahrenheit. Winds were at 30 knots, and this is our team member, John Friedrich, that's got basically an icing up problem there on the last day out of the field. So I think with that, I'll end my presentation. Thank you.
Thank you so much. I'm going to applaud that. I feel like I've learned so much about meteorites. I want to go like looking for some. Maybe I can identify some here in the Midwest based on your map. So I just want to remind everybody, please throw any questions that you have in our Q&A. I see some starting to populate. So the more we have, the better. And I am going to just kind of start. You did a really great job talking about how you use the skidoos or your walk. Can we detect meteorites using remote sensing or any other kind of more recent technologies that maybe we use in other parts of Antarctica?
Janie, do you want to comment on that?
Yeah. So, we're getting so much better at using things like satellite imagery and even drones. And actually, when Jim was talking about the Utah meteor that came through, the two of us went out to the salt flats and we're looking for pieces of the Utah meteor. And we're not used to walking across a white surface all day long and not finding anything. We found nothing. And I had a drone with me. And we did fly it out for a ways, but it's really hard to see anything, even just from a drone. It's hard to tell. So we find that people are the best at spotting stuff and getting out there on a snowmobile and spacing from each other just right so that you can see something this big, black against a white surface. Turns out to be the best way to do it. I know, I believe some programs are using helicopters to fly in low and grab the big ones, but they're not getting everything. There's no way they could do that from helicopters. And so, I mean, we still want to explore the use of these technologies to help us out, but in the end, to grab the most we can, and it can be up to like 50 a day, the best way to do it is just get out there on foot or on snowmobile.
All right, this is a boots on the ground science here.
Yes,
Fantastic.
absolutely.
So someone just asked a question that I also was wondering, so I'm very glad they did. When you see the meteorite, can you almost immediately tell where it comes from, whether it's that asteroid, the moon, or Mars maybe? Or, and you mentioned the one, you're like, oh, this is obviously the moon, but does it, can you kind of look at one because you've been doing it for so long and you're like, yeah, this is an asteroid, this might be Mars? Or is there further scientific study to really confirm and identify that?
Yeah, I'll just say that, like I said, about 90% of the meteorites are chondrites. And so they kind of typically take on that rusty brown exterior and kind of spotted rustiness from the metal grains that are in there. So you can kind of tell those, but for the most part, you have to crack open a meteorite and do some further investigation to really tell what it is. And so we kind of give our best guess estimate of what it looks like from the field. But really the intricate work takes place at Johnson Space Center in the Smithsonian.
Yeah, I might add one thing to that. Jim was talking about finding their lunar meteorite, and I helped find one of those too at a different time. But there was another season, the two of us were out, and we found a really, and I think there was a picture you had of there, a really big rock, and it had a giant white crystal in it and the black material around it. And all of us said, oh, for sure this is from the moon. And then we got it back, and this may answer another question. And you need to do detailed, what we call geochemistry, just to look very carefully at the chemistry of the minerals, and especially something that we call the isotopes. And so that's sort of like where you have some extra neutrons in a certain element. And, some of those things can sequester into different minerals or different rocks. And we can find patterns that describe very carefully the moon and Mars. We know that about the moon because we have samples that we actually went and grabbed, right, with astronauts. And then we can kind of start to make patterns for different bodies. Well, it turns out this one was not from the moon. It was not from Mars. It was not from any asteroids. And it's a very special class that's all off on its own. And we still don't know exactly where this rock came from. And what we could probably assume is it's from a body that used to exist, but broke apart and it doesn't exist anymore. So that was a really special experience for me to realize that.
For sure.
That's incredible. Like the unsolved mystery of this meteorite that you found. That is so cool. So as with everything when we talk about Antarctica, I mean, changing climate, warming environment, you know, we see reports all the time. I mean, and you are going out on ice covered spaces, and you know, the icy dynamics are being studied by many other researchers. I know you guys are not, but have you found, or are you anticipating, or is there, you know, preparation potentially for how climate change may affect meteorite collection, whether that be making it easier, making it harder, or somewhere in between?
Yeah,
Yeah,
that's go. Do you want to go first,
it's up to you. It's
Jamie?
up to you.
Go ahead.
Yeah, so there was a paper that came out recently, in fact, last week, I think, by a group, and one of the participants has been down with ANSMET to look for meteorites, and they've been focusing on this idea that the meteorites are pretty dark in color, and so that focuses, you know, you get more heating of something that's dark, and if you get enough heating, maybe that thing will just sink down into the ice.
Yeah.
And Jim and I have been to a couple places on our searches. We're way up in the deep field. This is high altitude. It's very cold. But sometimes we find these little melt ponds where rocks have sunk down. And I've looked down in there and thought, I mean, are any of those meteorites? Can we get to them? And it would be a big endeavor to really chip through like a couple feet of ice to get to them. So no, it's not really practical for us to do that on our field season. So this paper indicated that with increasing temperatures, and if those reach the deep field of Antarctica, that maybe there is a risk of some of the meteorites sinking through. And there needs to be a little more study on this, but that's a real line of thought that we need to consider for ANSMET. Like, let's go get them.
Yeah, well said, Janie. This, you know, we are way in the center of the continent, and when people study ice and ice dynamics, they're concentrating on the edges, the glaciers that are coming off Antarctica. So we don't see exactly the effects of warming that you'd see on the edges of the continent, but certainly we believe that you know, Antarctica is warming just like every place else, and this could be a problem in the future.
Yeah, so something to watch over time as seasons progress. We got a question a lot before our event when people were registering, and so that's, if I wanted to go see a meteorite, how do I do that? Where do I go? Do I just like go down to the library? Do I go to a university? Where do I get to see that? Yeah. Specifically Antarctic meteorites, because that's what we care about, right?
Yeah, so I'll go first here, and I think Janie can add some stuff. You know, the Antarctic meteorites are curated by the Johnson Space Center, and then they are basically long-term curated by the Smithsonian Institution. So there are lots of Antarctic meteorites, ANSMET meteorites at the Smithsonian. There's not many there's a few on display at Johnson Space Center, but that's more of a you know, closed tour kind of facility tour. But there's meteorites all over the country in little museums, natural history museums. Check your local planetarium. I know that the planetarium in Salt Lake City has the best collection of meteorites here. And then a lot of universities have meteorite collections. Arizona State, the University of New Mexico, the University of Arizona are some of the bigger ones that I can think of. Maybe Janie wants to chime in too.
Yeah, I'm pretty astonished at the private meteorite trade and how vigorous that is. Most of them are coming from North Africa, and they get purchased by different people. In fact, you can go purchase one. I was just at the Tucson Gem and Mineral Show, and if you want a fun experience, go down there and you can find a bunch of different meteorite dealers and buy your own little piece from outer space. And most of the time, those have been done in a pretty good way. The dealers that end up in Tucson are pretty good about the way they collect them from the people who have found them in their different locations. And what we always hope is, okay, I mean, are these being studied somewhere so that they can add to the library? because all of the Antarctic meteorites are required to be stored and studied through the US government. And you can actually request to get that meteorite and study it yourself, you know, afterwards. And so that's another way to do it, is you can study meteorites and get them that way.
Yes, I should know. Someone told a story in the chat here that they thought they found a meteorite, but it turned out to be a piece of rubber when it warmed up from being outside in Antarctica, and it was soft. So figured that was not going to be a meteorite. But we'll note that our research teams have all the appropriate permissions to remove these items off the continent of Antarctica, because that is a highly regulated area. So I do want to go quickly kind of just to the next step. So you talked about you're collecting the meteorites, which is fantastic. You've got them all, you know, maybe hundreds, right, in a field season you're collecting. Then what? So you've collected these meteorites. I mean, we talk about what, 60 to 70 papers a year, which is fantastic. I don't know if that's all coming out of your shop. Probably not. There's probably a collection of you guys. But what do you do with the meteorites after?
Yeah. So these meteorites are collected for the U.S. Antarctic Meteorite Program, which is, you know, we're the field team that goes and recovers the meteorites, but we also have organizations, the Johnson Space Center and the Smithsonian, namely, that will receive these meteorites. So they're shipped to the Johnson Space Center. They're opened in super dry conditions and sterile conditions. Then they are initially characterized. Like they'll say, oh, this meteorite is such and such a type. And that's as far as they'll go. Then twice a year, these new meteorites that have been freshly classified are announced to the scientific community around the world. And then scientists, based on those newsletters and the catalog of Antarctic meteorites, can study any meteorites they want. They just have to write a short proposal, and that's how they get allocated either bits of the rocks, the meteorites, or thin sections of the meteorites to do all kinds of studies. And that's where all those papers and all those studies come from, and all those collaborations from scientists around the world, free of charge.
I love it. I love collaboration in science, and it's great to hear that there are so many researchers that can kind of access this data or this resource globally, not just in the US, because that's definitely something we at the NSF like to encourage and support. So we're coming up on our time, so I'm going to ask each of you just one last look. We have questions, we didn't get to all of them, but is there one kind of takeaway that you want to give our audience today? What's, you know, the one thing about meteorites in Antarctica, about your work that you think people should know that maybe you haven't had a chance to speak to directly?
I could start and Jim could finish it off. I just think I feel so lucky to have been able to be a part of this program. It's hard to tell from the pictures. This sort of answers one of these questions, because it looks so beautiful and like, oh, this is kind of like, you know, up in the mountains in Utah during ski season. And it's not at all like that. It's very cold and forbidding. It's always 0 Fahrenheit. And then, you know, some days, oh, we're taking coats off. Gosh, what temperature is it? It's 0, but there's no wind. So it's 0 with wind all the time. And you have to work very hard to get all your layers on. It takes 20 minutes to get dressed every morning. You feel like an astronaut. And so I always feel like an astronaut when I'm there. You're so far away from everybody. Nobody lives there. There are no native populations in Antarctica because it's just not a place for people to live. So to me, it's the closest thing to outer space that's on Earth. And not only is it like outer space because it's so difficult to live there, but you find pieces from outer space. And the fact that those two things mix together makes this such a special place and such a special thing that we can go find objects that teach us about the universe, about our origins, the story of Earth, the story of the whole solar system, all encapsulated in these little objects. And it's such a fantastic program.
That's too good. I don't know if I want to follow that. I will say, I think I will, you know, I agree with all that Janie said. Antarctica is a special place. We're very lucky to get to do this. It's hard work, but certainly we think it's rewarding, and we think it's actually paramount for science to.
Oh, he froze.
He froze.
Ah,
We're on pins and needles.
I know. I want to know what's paramount for
Yeah, we
science.
want to know what.
We'll see if he
I'll
comes
get
back.
back in a minute.
The government
we
makes
go.
budgets and we
You
certainly.
froze on us.
Oh,
Yeah,
I
you froze a little
froze.
bit. They're paramount for science, and then we didn't hear anything after
Yeah,
that.
That's it.
okay. And I said, I just wanted to say thanks to the general public for supporting NSF and NASA science. And that is where our funds come ultimately from you, the people of the United States. And hopefully you believe these endeavors are for the greater good of the world and the US scientists.
Awesome. Well, thank you. Yes. We appreciate, and we appreciate all of our scientists who are so committed to the work that they're doing. I'm going to have my colleague throw up our last slide here, which is just going to be some resources for everybody. We've got our social media accounts at the National Science Foundation, as well as some websites that you can visit to learn more about the NSF, about the US Antarctic program, and about the Antarctic Search for meteorites. So please do keep a lookout for an email after this. If you have any other questions, feel free to reach out. We are so glad you were able to join us and hope that you have an absolutely fantastic rest of your Monday, wherever it is that you are tuning in from. So we'll leave this up here for a minute or two as folks hop off. And thank you.
Thank you.
Sarah,
Yeah,
so maybe we'll type some answers to some of these questions in the Q&A.
absolutely. Yeah, absolutely.
Okay, great.
So yeah, if people are still on, we can.
Yeah, go right ahead. Yes, especially if you
good.
were typing some as well. Yeah, we can leave this open for a few minutes. So as folks hop off. Yeah, lots of things. Oh, the South Pole was here. That was exciting. I love that.